Okay, I would like to invite the next speaker. Is Wang from Shandong University, China. Backward stochastic differential equations, guided generative model for cross-modality brain image synthesis. Okay, please.
Yeah, thank you. So let me share my screen.
Yeah. Last report is yeah. Okay, thank you for participation. Continue.
So it's my pleasure to present my recent work on a novel generative model guided by backward stochastic differential equations. So for convenience, I will refer to this one, the backward stochastic differential equations, as BSTEs throughout this talk. So this work is joint work with Professor Zeng Jingchen in Shandong University. And if you are interested in this topic, please be free to reach me via this email, please. Yeah. So at the beginning, let's first look at what kind of topic we are focusing on. Actually, this is a really meaningful and long history topic in field of medical and AI. So what is the medical imaging modalities? So it is referred to the different techniques used to visualize organs and tissues within the body. Some of the most common modalities include the X-ray, CT, MRI or ultrasound, and PET scans. So each of these has its advantages, and it is used for different medical applications. For instance, you can see that MRI provides excellent soft tissue contrast, while CT scans are preferred for bone imaging. So here is an example of the cross-modality medical imaging. You can see that first figure A, it shows the MRI to CT, and figure B refers to the MRI to MRI because there are different models, like this is T1W and T2W. W means weight. Yeah. So in this work, we will focus on this just for inside the MRI, but we use different models. That is to say, we look at how to transfer one distribution into another distributions. So we continue to look like why is cross-modality imaging important. We can see that the same disease can appear very differently depending on the imaging modality used. For instance, when we diagnosing the COVID-19, both X-ray and CTs are commonly used. But X-ray often can detect this, while the CT scans often provide better visualization of ground glass opacities. So this is critical in diagnosing the COVID-19, but much harder to observe in X-ray. So that is why we need to do this, because if we can use the findings in CTs, so we can observe this more convenience. Yeah, so this highlights the necessity of integrating information from multi-modalities for better diagnosis. We also look at there are two reasons for why we're doing this topic. That is to say, firstly, when we're acquiring certain types of medical imaging, such as PET and CT scans, or we always need to expose the patient to radiation risks. So this is particularly concerning when the patients require multi-scans over the course of their treatment, because they only have to require one pad. For example, we just we scan one time and we only get one type of model. So if we want to get multi models, so we need to scan multi times. So there is many risk of this. Part of this, second, due to the variation in imaging protocols and the high cost associated, it is often impractical to ensure that every patient receives a full set of imaging modalities. So this may result in missing or inconsistent data across different cases. So to address the above challenges, medical imaging synthesis provides a powerful solutions. It means that it aims to learn a mapping from available source images to generate corresponding images in another modalities. So you can say that it means in mathematics, it means that from a one distribution as to another distributions. If you are interested in this, you can look at these references. Yeah. Okay. As I just mentioned that in our work, we will focus on this one. This one is MRI. So we focus on this because this is widely used in brain research and benefits numerous applications. So there is many different modalities that is in the MRI. For example, there is 2-1-WI, that is to weighted imaging, and also the T2 weighted and also the CBA. So in the following, we will talk about how to maybe we transform the T1WI to CBA, and also maybe the T1WI and the T2WI to CBA. So that is our purpose. Before presenting the main models, let us first just a brief look like the generative models and BSDs. So generative models play a crucial role in cross-modality medical image. In recent years, several generative models have been proposed and widely used in various applications. So we can say, including the score-based generative models, that is a version of diffusion model, and also the Schrödinger bridge solve the question that maybe when the distribution is not a Gaussian nodes. So there are many work on this. But we notice that the key idea behind these models is to treat the image generation process as a continual probability distribution over time. So these evolutions, we also assume that it follows a stochastic process because we add the noise. Maybe it is a Gaussian distribution, so step by step. So we notice that the core task of these models to find an effective method for transforming one probability distribution to another. So this idea aligns perfectly with the formulation of forward-backward stochastic diffusion equations. That is why we use BSD in the following. So before introduce our proposed approach, we just look at the BSD because it is really related. So as for BSD, it is originally proposed by Bismuth as an adjoint equation for stochastic optimal control problem. Later, it was rigorously by Paduk and Peng. They established their existence and uniqueness under the Lipschitz conditions. So BSD has been found the extensive applications in mathematical finance, maybe including the asset pricing and portfolio optimization and risk management. So we can say this slide presents the classical formulation of BSDs. So we can see that this equation describes the evolutions of YT. But it is not forward in time, it is backward in time. So that is why it is called backward stochastic. Yeah. So we can see that it is driven by a function of G and also a ZT. Yeah. So we always call that J as the generator. And we also say that the thing is a given terminal condition as capital T. So we can see that YT and ZT is a solution of these equations. That is the difference between the stochastic differential equation, that is the forward in time. So many times we think that the ZT is like a control term. That is why we can from the Y0 to YT. This is YT is our aim, but ZT, like this process from 0 to T. So it is important to know that ZT is different. I think that these structures make BSD a powerful tools because it is in these terms. So we now continue to outline the most classical result of BSD. That is the key assumptions and fundamental existence and uniqueness theorem for BSDs. So we can see that assumption A1 ensures that the generator function G is well behavioral in the L2 space, and also A2, the assumption A2, this is a Lipschitz conditions. So this is a famous result that in theorem 1. That is to mean under this assumption, so we can say that as for the BSD above, it admits unique solutions. So with its development, we also see that many numerical methods. For example, we see that the deep BSD method. This is methods that combines classical BSD theories with deep neural networks to approximate unknown functions in equations. So you can see that this is a promising result in solving FBSD and in solving PDEs. So you can see that in this reference, it is published. It is published in PNAS, I remember. So that is maybe another paper. As we can see that based on the above, we can also notice that it is a nonlinear Feynman-Cut formula. So this result is also famous in the history of the BSDs. That is to mean that we combine a FBSD, that is to say this is a forward and this is a backward. We combine these two and to the relationship to the PDE. So that is to mean if we want to characteristic solution of PDE, we just need to use a BSD. So that is a famous result. Based on this result, we formulate our the main result, that is to say we recognize that BSD is a powerful tool for designing a pathway solution towards a future. So additional about the Feynman-Cut theorem indicates that BSD can facilitate the transformation between the distributions, because we can see that we can see that x0 and y0 and yt, there may be their relationship in there. So this naturally leads us to the question whether BSD could be leveraged to cross-modality applications. So in this work, we introduce BSD-based generative models for cross-modality brain image synthesis. So this is a novel framework that is from the perspective of K-ignorance. So this K-ignorance is a method of to measure the uncertainty. So we use this to characteristic the best situations and the worst situations. So this is used for the image-to-image task. We also use two networks to approximate the solution of the BSD process based on our about Feynman-Cos formula. So the performance of the BGM, we call it BGM because this is B and G and M. So we tested the performance of the BGM on the two data sets. The first is UCSF, the second is 721 MRI. So we also do three specific work, that is to say on the functional image generation and structural image generations. So we just look at the framework of BGM. So we can see that if we import the image, so this image may be the single modality or multiple modality. We import it into the X0, into the X0. So then we use a network. So this is the first network we use. Network is the aim is to approximate the solution of Y. So the next network is to approximate the solution of Z. So we use the first import X0 and second import this network, because this network is used to approximate the Y0. Or why we do this? Because Feynman-Cos tells us that the Y0 is a function of X0. So after using the OLA method, we can step by step, and then we can get the Y capital T. Yes, that is the terminal time. Only if we use these two networks. So when we get the terminal time, and we can compare with our real image, that is output image. So we just do this train and validations, so we can train best Y and Z, and then when we import another one, now we can do this line, and then we can get Y and T. So the Y capital T is our result. So overall, given an input image represented by X, so we also get a target image denoted as Y capital T. We established a connection through this forward and backward stochastic diffusion equation, that is BSDE. So that is through this system, and we characterize the analyze process. Also, with the K-ignorance principles, we formulate the following BSDEs. So we can look at this one. Yeah, this is the form we use. We can see that its solution comprises Ys and Zs from time S within the time 0 to capital T. During the training phase, we just use the Feynman-Cos formula and numerical solutions for BSD to contrast these two networks. And then in the generation stage, we employ the import image, and then along with this Ys and Zs, and to derive the value of Y capital T. So we notice that there is a difference between the existing work about the score-based generative models and the Schrödinger bridge. We can know that although there are some work, they may mention that the BSDE in this one, because they just use BSDE to approximate this. We just call it the score function, but they do not use the BSDE for the reverse parse. That is the difference between our methods and to the diffusion models or other existing work. So you can see that we do not use a reverse SDE anymore. We just use BSD in this time. So this is network. I will ignore this for the details. So there is three specific tasks. Let us first look at this. So the performance is just assessed using two data sets. First is open source. This one is open source, that is to call USSF. And the second one is this one. So the second one is conducted between the December 2016 and March 2020 in the Department of Radiology at the Shandong Provincial Hospital in China. So we also test the model's ability to generate both functional images and
Lou,
the structural.
are you hearing me? 3 minutes, please, left. Yeah, 3 minutes.
Yeah.
Okay.
Thank you. Yeah, I will go. Yeah. So the first one is task one, like this, is generated CBA, and the second one is generated DWI, and the third one is generated the T1W. So we just go through our result in the task one, because task 2 and task 3 is similar. So in task 1, we can say the first result is that this like the SSIM and also MAEM MC, they all have the good idea. So another result is that one we post on the specific patients, and we can see them, they are really similar. Yeah. So also the numbers and also it's great. So the second result is that we compare against the other existing work, we can see that this BGM is also the best. Also, the following result is about we do different BSD form, that is to say we like K to be 1 or -1, and we can see the performance at this. So we can see maybe for K equal to 1 is best, while K equal to -1 is worst situations. So this is task 1, and we do task 2 and task 3 at a similar time, and also have some results. This is the overall of this work. So maybe any more questions?
Yes. So are you finished? Yeah.
Yeah, I'm finished.
Okay, thank you very much.
Sorry.
Oh, congrats. It's the last report on this day. Yes, we have some time for short questions. Yana? Oh, okay. Come in. Please. Oh, just a minute. Need.
Okay. Yeah, thank you for your talk.
Yeah, thank you.
So there is a common problem in diffusion-based generative models that in sampling you have to do multiple steps, and it sometimes takes quite a long time. And do you have similar problems with your method, or is it possible to apply similar solutions in score-based models to maybe reduce the number of steps?
Yeah, that is a good question. So actually, it needs many times, but in this work, we just use 2 types. That is to say, we just use the 0 and 0.5 and 0.5 to 1. Yeah. So actually, in this work, we just use the 2 steps. As for the solutions, I think that is to BSD is different with the reverse time SDE. So that is to say, you can understand that reverse time is A to B, and then it is known to how to go and how to back. But BSD, it is another path. That is to say, if we go there, and we will find another way to go, but not the original way.
Okay, thank you. Thank you for your response.
Yeah, thank you.
Okay, thank you. Additional congrats, and I think we finished today. Wow, conference second day. It's the hardest 2 days was